head here. I'm in an area where I have a poor internet connection, so I'm not going to stream my face today, but many of you have seen it before, so you should feel comfortable. This is our first seminar for Nuclear Engineering 501. We have 12 seminars scheduled for the semester. Students are required to attend 75% of those, so 9 of the seminars. If you're not able to attend the seminar in person, you can watch the seminar later and send in a one-page summary through Canvas for the assignment to get credit for that seminar. If you attend the seminar, since we're using Zoom, I actually have a listing of who attended and how long they attended. You need to attend for at least 45 minutes. Most of these seminars are 45 minutes long, plus Q&A. So I'll go ahead and get on with the first University of Tennessee Nuclear Engineering Departmental Seminar today. And we're very lucky to have one of our own. Lieutenant Commander John Baker is an assistant professor at the United States Military Academy at West Point in the Department of Physics and Nuclear Engineering. He earned his Bachelor of Science in Chemistry from the U.S. Military Academy in 2001, a Master of Science in Physics in 2010 from the University of Alabama in Huntsville, and a PhD in Nuclear Engineering from the University of Tennessee in May of 2020, so he's a fairly new grad. His previous duties include teaching physics at the U.S. Military Academy, teaching the Nuclear Weapons Orientation course and the Theater Nuclear Operations course, and serving at USANCA. And USANCA is the U.S. Army Nuclear and Countering Weapons of Mass Destruction Agency. Before becoming an FA-52 nuclear CWMD officer, so that's a Countering Weapons of Mass Destruction officer, he served as an Army aviator, both with the 82nd Airborne Division and the 101st Airborne Division. So welcome, Dr. Baker.
Thank you, sir. Can everybody hear me and see me all right?
We can.
Yep,
awesome.
hear you well.
Thank you. All right. So I'm going to go ahead and start the slideshow here and share my screen. Just a second. And now I want to share screen. All right, and so now everybody should be seeing the introduction screen, correct? All right, awesome. So thank you, Dr. Hines. Thank you to the faculty there at the University of Tennessee for this opportunity. And I appreciate all the students. I know you don't necessarily get an option to be here, but for those that are here, I appreciate you. Please, hopefully you get something out of this, and let me know if you have any questions as we go along. So this is the title of my dissertation, Remote Measurement of Multi-Axial Contraction due to Pressureless Sintering. And I have scaled it back quite a bit from the actual dissertation, but hopefully you'll be able to get something out of this. So some of the motivations for this research, basically the general purpose heat source was kind of one of our main motivations. You know, when you're looking at nuclear fuels and the formation of different, whether it be fuel pins or like the general purpose heat source, sintering of ceramic powders is the method for making those objects. And so I wanted to kind of understand some of the science behind that a little better. Also, there are some potential applications for advanced reactor, advanced fuel forms that perhaps would benefit from being of a lower density. So that also played in. The research was really focused on either plutonium oxide or uranium oxide. However, both of those things obviously are not easy to work with due to contamination, those issues. So ceria or cerium dioxide was chosen because of its ceramic suitability. So essentially it behaves much the same as plutonium oxide. So I've thrown the word ceramic around a little bit, kind of wanted to not insult anyone's intelligence, but at the same time make sure everybody's on kind of the same page. What do I mean by ceramics? Obviously, most people are familiar with things like potteries and glass and porcelains. Those definitely are ceramics, but more than that, there are a lot more to ceramic science than that. Essentially, metal oxides, metal nitrides, metal carbides, borides, all of those things are ceramics, and they have applications in literally 1,000 different applications in everyday life, from resistors to semiconductors to superconductors to thermal insulators. Ceramics are literally everywhere. Typically, the way ceramics are formed is they go through some type of shaping, some kind of size, an initial preparation, if you will, to get the initial object ready, and then they are heat treated. That heat treatment imparts a structural change in the microstructure of the object, and it increases the strength. It changes all of the properties, to include the resistance, the mechanical properties. All of those things are changed by this heat treatment. And so generally, sintering of powders is done, it's a polycrystalline ceramic. It also loosely applies to amorphous ceramics, i.e. glasses, but really my work was more focused on the polycrystalline ceramics. And again, when you talk about that sintering, that heat treatment, what we're really trying to do is we're trying to activate mass transport events. And these mass transport events seek to or bring about densification, reorganization of the crystal matrix, pore elimination, densification. All of those things happen during sintering. The object, once it's formed, no matter how it's formed, it is referred to as a green body before it undergoes the heat treatment, and then it's called the sintered object after heat treatment. So this is a very wide process. The process of forming a green body and then sintering is widely used in industry. In typical industrial processes, the green body is formed through one of many different methods. So there's slip casting, there's tape casting, there's extrusion, there's molding, axial pressing, isostatic pressing, and the list goes on and on. Multiple different ways to form the green body, and all those different forming processes have different effects on the actual structure of the green body. Most industrial processes do something to the green body before they heat treat it that results in approximately 40 to 50% theoretical density of the green body. And then during sintering, it goes anywhere from 60% theoretical density up to 100% complete theoretical density. This work specifically was looking at much lower density ceramic objects. So my work was focused on loose powder sintering, i.e. I literally just poured a ceramic powder into a crucible, scraped it level, and put it into a furnace and tried to see how sintering, what effect it had on the object. The other thing that was kind of unique to my work was I attempted to use the master sintering curve to see if I could predict the sintering behavior. So could I model that sintering response function and predict, based on certain parameters of the powder, how objects would sinter up and how they would densify. So again, not to belabor this too much, but in general, sintering is a mass transport. You can see from the slide there are at least 6 different mechanisms. Not all of them are necessarily applicable. Plastic flow specifically usually is only associated with the sintering of metals or glass powders. When you're talking polycrystalline ceramics, you're really only talking about those first 5, so surface diffusion through lattice diffusion. But essentially, during heat treatment, mass is moved from either the boundaries between particles or the interior of particles, and it moves to the joining surface between where those 2 particles or 3 particles touch, and necks are formed. So matter is moving from one place to another, and that's how those pores are eliminated and densification happens. So just kind of the simplest model is the 2-particle model. You can see the 2 particles on the top left there both have a diameter. And so the driving force for sintering is the reduction of surface energy or minimization of surface energy. And so the surface area of those two particles is much, much larger than the surface area of that coalesced single particle down at the bottom with 1.26D. Again, that minimization of surface energy is the driving force behind sintering. So again, there are lots of sintering methods, lots of processes for sintering. Specifically, my research was focused on pressureless, solid state, single phase sintering. So I never got the powder close to the melting point. There was never any creation of a liquid phase in my crucibles. It was all solid state. Just pour the powder in loosely, and solid state processes took over during sintering. There you can also see that during sintering, there are really kind of two competing processes that happen. One is densification, which really involves the particle centers moving closer together and the elimination of pores. The other is coarsening, which also is referred to as grain growth. These are competing processes. Densification is a good thing in general. That's what you're trying to have happen. You're trying to avoid coarsening or excess grain growth. These are the 4 stages of sintering, classical sintering, and usually the initial, that loose powder or stage 0 is not really, there's not a lot of literature about it. It's not really referred to. Really, you can't find a lot of information about it other than, hey, this is, you pour the powder into the crucible before you start your green body process, and that's loose powder sintering. My work specifically focused on loose powder in initial stage. So rather than doing something to the loose powder, either pressing it or extruding it to try and increase the initial density before sintering, I kept it at very low densities. So most of my samples started out at somewhere between 10 and 20% theoretical density, and during the sintering process densified up to approximately 30 to 40% total theoretical density. So I never even got out of that initial stage sintering. Really, to go from initial stage to either intermediate or final stage requires either the application of pressure or a much longer sintering trial. So you got to get it up to a very high temperature and hold it for a much longer period of time. Again, this is just kind of the same information presented in a slightly different way. So it kind of points to some of the descriptions between stage 0 or loose powder sintering and stage 1 sintering. Again, intermediate and final stage sintering, those are more associated with industrial processes. When you talk about the sintering of ceramic nuclear fuel pellets, that they are sintered to approximately 95 to 100% theoretical density. But that's done under very high temperatures, very controlled atmospheres, and usually lots of pressure applied either before or during the sintering process. So I know that looks pretty awful on the screen there. This is the master sintering curve. But really, I just want to call your attention to kind of how this works out. So that top equation is derived from the combined stages sintering model. Again, just like methods for sintering and processes for creating green bodies, there are a multitude of models to try and predict different sintering processes. Usually they only apply to one or two stages of sintering. The master sintering curve, or the combined stage sintering model, is unique in that it applies to all 4 stages of sintering. So that was kind of the starting off place for this theory. The master sintering curve took the combined stages sintering model, that top line there, and used separation of variables to move everything that is a function of density to the left-hand side and everything that is only a function of temperature to the right-hand side. And so by that separation of variables, you get these 2 equations that are equivalent. So the equation in the middle here is everything that's a function of density, and it's pretty complex. It requires some measures of things like packing parameters, densities, and it's not trivial to make those measurements. However, the equation at the bottom is fairly straightforward. It only depends on time and temperature. Q is the activation energy, which can be estimated and empirically determined. That's the R is the ideal gas law, or so it's the gas constant. But you just have these two temperature values and time, total time that the object is centered. And so that integral actually turns out it's pretty easy to perform. And so you can really kind of use this model to predict centering behavior. So if we look at this, this again is using the master centering curve to try and make some of those predictions. So the chart on the left shows multiple different centering trials at different heat rates, and you see that the relative density on the y-axis and the temperature on the x-axis, you can see that the different heat rates achieve different relative densities as a function of temperature. So, you know, the faster we heat it, the more quickly it densifies, essentially. Or the less dense it is at the same temperature, maybe is a better way to say it. But what's interesting is by taking that set of data and applying it through that equation that I showed on the previous slide, those curves all condense to one curve. That's the graph on the right. By plotting the log of theta, which again is that equation. Let me go back one slide. That equation right there. We take this parameter theta, we solve for that parameter, and then we plot the log of theta versus the relative density, and all of those curves come together as one curve. That is the master centering curve for this particular green body process and this particular ceramic under these centering conditions. So no matter what heat rate you use, ostensibly anywhere between 8 degrees C per minute and 45 degrees C per minute, you can use this curve to predict how this alumina is going to center. So there's actually some literature that shows that the master centering curve method does work reasonably well for cerium dioxide. However, I want to call your attention to two things here on this slide, and then we'll compare and contrast those with my own results later. This work starts out at approximately 60% theoretical density. So again, as I mentioned, in industrial processes, you know, the powder is poured into some mold or crucible, but then it's either pressed or tapped or vibrated, somehow subjected to an initial densification process prior to sintering, so that all of their sintering curves start out at approximately 60% theoretical density and go up to approximately 90% theoretical density. The other thing is their activation energy is pretty high. Again, it corresponds pretty well with the literature. However, that's not what I found during my research. So some of the known issues with the master centering curve, the initial steps of the master centering curve, some of the assumptions that are made in order to take the combined stages centering model and arrive at the master centering curve is it's assumed that the shrinkage is isotropic. That enables you to take the change in length with respect to time and turn that to a change in density with respect to time. If all the shrinkage is the same in every direction, then it's just change in density. It turns out that if that's not true, the master centering curve might not actually be applicable. Another problem with the master centering curve is it assumes that only one diffusion mechanism is dominant during that centering trial. The problem with that is the different centering mechanisms have different methods of transport for that mass transport, and so it has a different activation energy, so that the Q might not apply to multiple different diffusion mechanisms. It's not very useful for low heat rates. When you use really low heat rates, you tend to see a rapid grain growth, and so that kind of works against densification. And again, as I've kind of already mentioned, but just want to highlight, it's only valid for the same green body process. So if I pour the powder in, you know, to this size crucible from this height, and it's this size powder, and I center it, as long as I keep all of those things exactly the same from trial to trial, the master centering curve will apply. As soon as I change either the particle size or the applied pressure, or anything else that I'm doing to the green body prior to centering, once I change any of those variables, then I've changed the green body process, and so the master centering curve won't apply to that new process. So speaking specifically about isotropic shrinkage, Hans Eckert Exner published some work. Specifically, he was looking at metallurgy, so he was looking at sintering of metal powders, but the science is the same. So he proposed that if you see shrinkage, which is anisotropic, i.e. it's not the same in every dimension, then you had, he proposes one mechanism that could cause that is pore elongation. So whatever you do to the green body prior to the onset of sintering, if you're pressing it axially, you could elongate the pores in an axial direction, which could then lead to greater shrinkage in the axial direction, vice the radial direction, and cause that shrinkage to be anisotropic in that way. The converse of that is also true if you apply pressure isostatically, so equally in every direction, you could cause the pores to be elongated preferentially in the radial direction, which would lead to more shrinkage in the radial direction versus the axial direction. I took this value of delta R over delta A that Exner talked about, and I just assigned it a parameter, so I could just always refer to it that way. I chose the variable chi just because I wasn't using it for anything else in my work. So chi represents the change in the radial dimensions divided by the change in the axial dimensions, or the radius versus the height, if you prefer, of a cylinder. So this is just some data that I was able to obtain from some industrial work. You know, Oak Ridge is a great location, University of Tennessee. They're ideally situated to kind of interface with some of the industries that are important, a lot of the work that we do. So I was able to actually get some of this data from Dave Johans. And so just looking at this, what he's showing here is that an object that they took an aluminum oxide object and they uniaxially pressed it so that it had the same dimensions in the radial and axial direction. So it was a perfect right cylinder with, for example, if the radius was 1 centimeter, the height was 1 centimeter, right? And then they centered that object, and they did this for multiple different trials with multiple different applied pressures for their uniaxial pressing. And what they saw was that there's this trend that the more pressure that was applied, you know, obviously the more it shrank in the axial direction. But also, no matter what, there was this inconsistency, this gap between the shrinkage that they saw in the axial direction versus the radial direction. And so on the next slide, I take that same data and I plot this chi value, so the ratio of delta R to delta A, versus, you know, the ideal situation that shows isotropic shrinkage. So if it shrank the same in both dimensions, it would be along or very near this dashed red line, which is isotropic shrinkage. But as you can see, chi is much, much less than 1 in this case for uniaxial pressed objects. So that was an interesting starting place. I was also able to acquire some data about isostatic pressing. So the same process, the same material was used, the same kind of, you know, we're going to apply pressure to create the green body before sintering. Only this case, instead of uniaxial pressing in only one direction, it was put into a wet bag and isostatically pressed equally in all directions. So here, now we see that the radial component actually shrinks more than the axial component, which, as you can predict, leads to a chi greater than 1. So kind of very interesting to me, at least, not knowing a lot about ceramic processes before I started this research, that depending on how you process the green body before you sintered it, you could see a drastic shift in whether the shrinkage, the densification, was isotropic or whether it was anisotropic. So then that led me to some of my work. I'm trying to look at, again, whether I can use the master sintering curve to predict how the sintering of ceria dioxide, how that works. So I came up with a couple of different kind of test stands, test designs to look at how sintering progressed. One was a dual pushrod sintering dilatometer. First of all, I looked at some previous testing, and then I also, you know, I used a dual pushrod sintering dilatometer, and then I also wanted to see if that was able to capture the sintering response. And so then it came to light that I was going to have to kind of build something that didn't really exist. So I'll talk about that. So kind of the design of experiment, these are just kind of the max and min parameters that I was using for all of my data. You know, I used heat rates as low as 0.1 degrees C per minute, but again, I had a lot of problems anytime I got below 1 degree C per minute. So a lot of that data just had to be kind of ignored because of the excessive grain growth. As far as dwell time, that's really just how long I held the ceramic object at temperature once I got it to temperature. I looked at values between 60 and 180 minutes, just really because anything longer than that started to become, kind of difficult to get to. If you're heating it at only 1 degree C per minute from 20 degrees C up to 1,100 degrees and holding it for longer than 3 hours, very quickly it becomes, a 10, 11, 12-hour day. And then finally, powder specific surface area. That's just a way of kind of classifying the particle size of these powders. So specific surface area, if you're familiar with it, we use the BET, the Brunauer Emmett Teller design. We had a system that would actually calculate the specific surface area. So that's just a way of saying that I had powders that ranged anywhere from very, very small particle size, nano size particles, all the way up to very large objects. So here's kind of you might be more familiar with the D50. That's the, if you take a plot of all the diameters of all the particles, the particle size distribution, D50 is the most likely diameter. So the 4 different particles we used had a D50 all the way down from micrometer, or hundreds of micrometers, all the way up to 30 micrometers. Again, this is just kind of comparing those 4 different particles that we use: the nano, the SPS, the RPS, and the LPS. Again, the previous slide showed the D50. This is comparing the specific surface area using the Brunauer Emmett Teller theory. And that piece of equipment, again, is called the TriStar 2 automated porosity analyzer, if you're familiar with those. So some of the previous work that was done before me was what we call a quench test. The samples were created in these crucibles, placed inside an oven, multiple samples at a time, heated up at a controlled ramp rate and held at a dwell temperature. During heating, the door would be open to the furnace, sample would be pulled out, photographs were made, and then the sample was dumped out to quickly cool down so that you could kind of make measurements of the changes in the specific surface area, the porosity of the object. The problem with this, as you can clearly see that there's a lot of densification happening, a lot of shrinkage of the object. The problem is it's very difficult to quantify. It's tough to actually get your arms around how much did the object shrink and at what point did it shrink. Did that shrinkage happen in the last 100 degrees C? Was it constant throughout the entire sintering process? At what point did sintering onset? At what point did it stop? So very difficult to answer those questions just by looking at post-mortem analysis. If you can't look at it while sintering is occurring, it's tough to really say what's happening when. So to kind of get after what's happening when, I started using a dual push rod sintering dilatometer. So essentially all this is saying, a dilatometer, for those of you who aren't familiar, it just has a very, very precise LVT. So it's got a pressure transducer that tracks a sensor, and the sensor is attached to a push rod, and the push rod sits on top of your sample. And so it just measures how the sample contracts as a function of time and temperature. The dual push rod sintering dilatometer actually has 2, and so the second push rod sits on top of the crucible that the sample is contained within. And so in that way, it's able to subtract out any thermal expansion of the system writ large and only look at how the sample itself actually contracted. So this is a pretty precise piece of equipment, makes really great measurements. However, the problem is it's not able to capture how the object shrinks in multiple axes. It only captures that one axial direction. And so if the shrinkage is isotropic, you can take the ratio of the length at any point in time to the original length and apply that to the radius, and that works fairly well. But if the shrinkage is not isotropic, then it really doesn't work so well. So how can you capture the shrinkage of a 3-dimensional object inside a furnace at temperatures up to 1,000+ degrees while it's actually sintering? Turns out, best way to do that is using radiography. So by creating a biaxial oriented radiographic imaging system, I was actually able to image the furnace while it's heating at multiple steps during the heating process, and so actually look inside the furnace without disturbing the contents. So here's kind of some of the CAD drawings of what we wanted to build. Here's a photograph of the actual design built. You can see that this panel appears to be able to slide. So also does this digital panel. So the whole system is comprised of a thermo-scientific furnace. There's a Novo 22 digital X-ray panel. There's a XRS4 digital X-ray tube. But these panels were initially designed to be able to slide in and out. That way you could do some geomagnification. Turns out after running not very many tests that it was very quickly determined the way for these images that we were creating, these radiographs, to be as usable as possible, to have the best resolution, you really needed to get that panel as close as possible to the sample, and you really needed to get the X-ray generator as far away as possible. So I completely redesigned the system, and Boris ended up looking like this. So there are two XRS4s, one mounted on the floor, firing down through the front of the furnace. The second XRS4 mounted approximately the exact same distance up in the air, 6.5, 7 feet in the air, aimed down, firing through the top of the furnace. I also had to change the furnace because of the location of the heating elements in the other furnace. The other furnace was much more efficient at heating and controlling the temperature. However, that did not make for very good radiographs. So this configuration yielded the most usable radiographs and was able to provide the most information, the most bang for the buck. So this is the system that I built. So some of the materials and methods that I used, again, this is just some of the crucibles that I used in the sintering dilatometer. So I used a high purity aluminum oxide. The Syria powder was poured loosely into the crucible, and then I placed the small disc on top just to keep that push rod completely level on the top of the powder. And then the push rod rode on top of the powder. And so as the powder contracted, the push rod moved, and it was able to make very precise measurements of how the powder contracted as a function of heat and time. The crucibles used in Boris, similar, slightly different. So I also took aluminum tubing and just cut it into sections, and then I used super glue. It's useful to, at room temperature, to kind of position things where you want them. And then during the heating process, the super glue actually just burned away and had no effect. But again, both of these are just ultimately flat bottom right-sided cylinders. And so, we can talk about the different volumes used and things like that, but these are the crucibles that I made for use in the Boris system. Also, during the part of my experiment, I started to have some concerns about the error analysis. And so at some point I decided to look at a larger crucible. If your ability to make measurements stays the same, however, you're looking at a smaller object versus a larger object, well, then your error analysis goes kind of haywire. So by looking at larger centered objects, it kind of cut down on some of that error analysis. As far as sample preparation, again, these 4 different crucibles shown here, so are 4 different powders. So this top left is the LPS, the largest particles. The next one is the RPS, regular particle size, small particle size down to the left, and then last is that nano powder particle size. Other than that, the powders are essentially the exact same. It's all Syria dioxide with very minor co-contaminants. The different colors are just a function of slightly different combinations of contaminants and particle size. This is a view for the inside of the furnace that I was using. As you can see, the heating elements in this furnace are located on the sides. So it was perfect actually for making radiographs, kind of in situ measurements of an object inside this furnace, because the top and the bottom were both very clean, free of heating elements. So very conducive for making radiographs. The back side of the furnace, I was actually able to take it apart. So the control portion of the furnace is off to the right here. Power was applied through this, and I used multiple different thermocouple extension wires so that I could actually monitor the temperature, it was all under control from outside of the X-ray vault. So that way I didn't have to be near it while I was firing X-rays at first. The XRS-4 system, for those of you who are not familiar, it's a tungsten target, 370 keV Bremster lung source. So this is just that typical X-ray Bremster lung spectrum for tungsten. It doesn't show a 370 keV, but you can see that it follows a pattern here where the most likely energy, or the peak of this spectrum, is approximately 1/3 of the max energy. So again, for a 370 keV X-ray source, we would expect that the peak for that was at approximately 123 keV. It's a pulse source, so it's controlled remotely. You're able to turn it on, and it fires 199 pulses max every 10 minutes. And so, you didn't want to get any scatter between the two axes, so I would fire one axis, and then as soon as it was done, I would fire the other one. So here's an example of what those radiographs look like. This is before any processing or any kind of zooming in or looking at exactly what I needed. You can see I have the reference there. We call that a fiducial. It's just an object whose size is known. That's a high purity piece of aluminum oxide. It's an aluminum oxide sphere. So its thermal expansion properties are well known, well documented. And so knowing the temperature, see the thermocouple here extends and comes down and touches the surface, knowing the surface temperature there, and able to look at the size of the aluminum oxide sphere, I was able to very accurately, predict what these measurements were. So that's how I use that fiducial to kind of arrive at what the particle, or what the sizes of the sintering object was. I used ImageJ software to make those measurements. That's pretty much it for the materials and methods. So finally, the results, kind of what I was after. So what I noticed in my work was that no matter what I did, my chi was always less than 1. And so for loose powder sintering specifically, there was nothing I could find that would cause that shrinkage in the radial direction to ever be as much as the shrinkage in the axial direction. It always shrank, no matter what it did, it always shrank more in the axial direction than radial direction. So this graph here is predicting 2 different heat rates of the nano size powder in the Boris system. On the x-axis, or on the y-axis here, I have the axial shrinkage. On the x-axis, I have the radial shrinkage. Again, this dashed line, this green dashed line, is the isotropic case, but you can see both data sets are shifted significantly above that isotropic case. Here they are plotted. This is chi plotted on the y-axis, so that delta R over delta A versus temperature. So what this is showing is that the slopes of the sintering processes was very similar for both heat rates. It didn't really matter which heat rate was used, and I saw the same for 10 degrees and in between heat rates. The slope of the data set didn't significantly change. However, the sintering was delayed. The onset of sintering was delayed. It started at a higher temperature when I used a faster heat rate. When I looked at comparing data, so this is master sintering curve data from the Boris system versus the sintering dilatometer. Again, I found that the data was very, very comparable. They weren't exactly the same. Obviously, the equations were slightly different, but all of the data was very close within the margin of error, depending for the different heat rates from system to system. Hard to kind of figure out right off the bat what some of those reasons might have been for the difference between the sintering dilatometer and the Boris system, but I'll talk about that towards the end. Specifically, when I zoomed in and kind of looked at where those sintering rates were linear, I saw that, again, that fit of the data, that linear regression, was almost identical for multiple different heat rates. So you can see here, these are different trials of the same heat rate, and then 3 different heat rates. So total of 6 different trials. remarkably similar slopes of those lines of best fit. R squared values almost 1 in every case. So the data is pretty good. But again, there is that shift, that delaying, for lack of a better word, of the onset of sintering. So the faster you heated it, the less dense it was at the same temperature. So just some of the conclusions that we were able to draw from this. Anisotropy turned out to be a very significant factor in this. You know, it was unclear starting out whether the shrinkage would be completely isotropic and the master sintering curve would work like gangbusters, or if it was going to be a much bigger problem. The industrial data seemed to suggest that anisotropy was going to be something we were going to have to work through. It turned out to be the case. As far as the cause of the anisotropy, it's still unclear what all factors go into that. The problem with sintering theory is there are literally so many variables that apply and could have a significant impact on that green body. And so if it's not exactly the same from trial to trial, you get some kind of random errors thrown in there. But even if those green body processes are the same from time to time or from trial to trial, something is causing either, you know, if you subscribe to the Hans Eckert theory of pore elongation, something is causing the pores in that loose powder to be preferentially elongated in the axial direction. And it's unclear, at least for my work, what those factors are. This is just some of the factors that could be a cause. As far as that delayed onset of sintering as a function of heat rate, you know, we posited several ideas. Was it possible that it was thermal lag? You know, just we're heating it too fast for the center of the ceramic object to actually see the same temperatures as the rest of the furnace. But we did some finite element analysis modeling, and it turned out that unless you're talking about 100 degrees C per minute or higher heat rates, that thermal lag really isn't a factor with these small objects. Obviously, if you're sintering an object the size of, you know, a large oven or similar, a large brick tile, maybe thermal lag might be an issue. But the volume size of all my samples was so small, you know, approximately a cubic centimeter on the smaller crucibles, that thermal lag really wasn't an issue at all. Additionally, some of the conclusions, the master sintering curve just appears not to be able to quantify or accurately predict the anisotropic shrinkage. And overall, it was able to model very well the actual densification of the object if you ignore any densification gradients and just look at the total density of the object. So it was very successful at modeling and predicting that densification. However, because the shrinkage of these objects was anisotropic, it shrank more in one dimension than the other, the master sintering curve isn't able to capture that. It isn't able to predict that at all. And so if you need an object that's, you know, precise in its measurements after it's sintered, then it's very difficult to see how the master sintering curve will enable you to predict those shrinkage, that anisotropic shrinkage. So, subject to your questions, that's all I have. I don't know if anybody was looking at the slide counter, but there's a total of 112 slides in this deck. I hid most of them. If there's something specifically you have questions about, I'm sure I have a slide that talks about it from my defense. And I'm also willing to, as long as Dr. Hines is willing to let you answer questions about either the United States Military Academy, where I currently am stationed, or the Army in general, or being an FA-52, or any of those kinds of questions. So I'll open it up to questions and shut up for a second. Thank you all for your time.
Yeah, so it's open for questions. If you have a question, just please raise your hand. I think that'll pop you up on my screen. So Dr. Baker, I have a question, and I don't know if you can answer it or not. I don't know if you can, you know, kind of speak around the edges, or, you know, think your PhD dissertation was classified, so it's not published, and that's fairly common for FA 52 officers that come here and then do a lot of research out at a skiff at Oak Ridge, and then have 4 or more cleared faculty or people in your dissertation committee that already have clearances, and it's all done kind of what's done in a classified space. Can you make any comments on how this research can impact, how this information can be used to impact anything in industry or anything else? What could be some of the impact of this knowledge? How can some of this knowledge be used?
Yes, sir. Yes. So again, I don't have any direct applications for the research, other than the only thing I know of for certain when you would want to sinter a ceramic object purposefully to have a lower density, some of the ideas that we came up with, diesel exhaust filters are a porous ceramic. And so currently the way those objects are made is they introduce I can't think of the exact name, but they introduce a filler basically that takes up, that creates voids in your ceramic object as it sinters. And then once you're done sintering the object, either those fillers either melt and pour out during the sintering process, or you have to do something additional to the object after its sintering is complete to kind of get those objects out. But that's currently how porous ceramic objects are made, that something else is introduced that then has to be removed. The thought was that, this method of loose powder sintering could be used in theory to create porous or lower density ceramic objects, like a diesel exhaust filter. The other idea we had, and again, this is more speculative in nature, but who knows what new and improved, generation 4, generation 5 reactors may be conceived and thought of in, 10, 20, 30 years from now. And so, a lot of the issues with the liquid metal fast breeder reactor project out at Oak Ridge specifically, you had a lot of fuel relocation. So during fuel cycles or during operating cycles, the flux was such, the temperatures experienced by the fuel was such that, you'd get fuel that would move around within the fuel pen itself. Obviously, you don't want that inside your reactor. So it's conceivable in the future that there could be a need to have a less dense starting out fuel pellet, whether that's uranium or plutonium oxides. So this is just looking at, rather than pressing that pellet ahead of time, whether that's uniaxial or isostatically to create that green body, would it be possible to create a nuclear fuel pellet using a loose powder methodology? That's really kind of what we were thinking, sir.
Yeah, I know that, Dr. Kane Ang, has a materials, a fuel fabrication lab in SURF that does sintering and development of advanced fuels that are more fault tolerant. And, their goal seems to be, exactly the opposite. They want high density,
Right.
a lot of uranium or whatever the fuel might be, and they make these ceramic fuels for the high temperature applications, maybe nuclear thermal propulsion and other high temperature reactors. So it's interesting. It seems like you find some creative person at some point, and he finds out that something is exactly the opposite. Might actually be beneficial to whatever they're doing. So that's interesting. I think Brian Cowell has a question, so I'll turn it over to him.
Yes, sir. I was reading Mr. Cowell's question there. As far as, so specifically, if you can't see the chat, he's asking, do I have any suggestions for isolating the possible variables which affect the anisotropy, would sifting the powder into the crucible rather than pouring it some change of that height versus diameter, aspect ratio of the crucible, and then trying some other non-cylindrical. The crucible doesn't have to be a right-sided cylinder. That just lended itself well to the kind of the Boris. I was able to assume radial symmetry, so I really only needed to capture 2 axes instead of trying to get a 3-dimensional or a 3-axis radiography. So yeah, another way to kind of think of isolating those things. I would think there needs to be some mechanical process of creating the samples, and whether that's something that needs to be more repeatable, I would think would be my short answer. Just because my methodology of pouring from a bag that contained the powder into the crucible, it might not have been the same every time. It might not have been pouring from the same height every time. I did try sifting these powders, but again, the powders are so small, first of all, and so it takes a long time to sift these. Like I'm talking, when you make a larger crucible, it would take me an hour sometimes just to sift the powder. And they agglomerate. They're hygroscopic, so they pull water out of the air and they clump together. I've tried drying it before I did that. It really didn't seem to help. I did conduct multiple experiments with different crucible sizes and shapes. So I used one that was more like a hockey puck shape, so much larger in diameter than it was high. The problem with that size shape crucible was I tended to see a lot of cracking. I had trouble keeping the centered object together. Industry showed us that you can literally make almost any size, shape object you want out of ceramic as long as you apply the right pressure before you apply the right green body conditions prior to sintering. And so I'm confident that if I somehow pressed and made a hockey puck shaped compact green body before I sintered it, that it would sinter just fine. But pouring loose powder into a hockey puck shaped crucible and scraping it level, I saw a lot of issues with that. So that's what kind of drove me in my condensed timeline to go to the right-sided cylinder. It seemed to work. I didn't have any more trouble with cracking. Obviously, you could go with rectangular. You could go with spherical. There's all kind of other shapes you could choose. I was just trying to simplify the math and make sure that I had some kind of symmetry. So I was really only concerned with 2 axes. But yeah, there's got to be a sample production. How you make your samples, I think, was the biggest source of random error in my data. And so if there's some way, any methods, and I would default to a ceramic engineer, somebody who does this all the time. What mechanical methods can we use that will ensure that sample preparation is done the same day in, day out, and so just eliminate that source of random error. Did that sort of answer your question, sir?
Yes, sir. Thanks, Colonel Baker. It's good to see you again.
Thank you, sir. And again, I'm willing to answer any questions if you have questions about the United States Military Academy here at West Point, or being an Army aviator or an Army FA-52, or kind of what FA-52s do in the Army. Whatever questions you'd like to ask. My time is yours for the next 8 minutes or so.
Go right ahead, promise.
What's that, sir?
Yeah, I have a question. What are FA-52s? I actually don't know, and I would like to know what they are and what they do.
Sure, great question. So when you become an Army officer, when you go either to ROTC or I graduated from the United States Military Academy, everybody goes into one of 16 basic branches: infantry, armor, aviation, field artillery, and those branches determine what your job is, for lack of a better word, in the Army. So I was an Army aviator. I flew helicopters. Specifically, I was a scout pilot. I flew the little 2-seat Kiowa Warrior helicopter, the one that's got the little ball on top. And so I was an Army aviator for the first half of my career. at about the 10 to 12 year mark in your Army career, you have to make a decision whether you're going to stay in that basic branch and continue to try and be a commander. You know, I want a battalion commander, brigade commander, try to become a general officer like that. Or do you want to do something more technical? And so the Army kind of chose for me, because that was about the time in my career that the Army decided they were getting rid of the Kiowas. The Kiowas went away. We flew them all to the Boneyard in Arizona, Tucson, Davis-Monthan Airfield, and they're all parked out there in the desert. So all the Kiowa pilots had to find something else to do. So I already had a master's degree in physics. I had already taught physics at the United States Military Academy. So I was looking for something that was more technical that I could do to kind of finish out my career. So when you switch to that more technical track, that is considered a functional area. And there are many different functional areas in the Army. One of them is a FAO, a foreign area officer. So FAOs typically are trained in a specific language. They receive training on a culture. And so we have FAOs who are stationed at embassies all around the world. So the U.S. Embassy to Macedonia, there is an Army FAO officer, probably a major or a lieutenant colonel like me, who is stationed in that embassy, and he works with the local nationals. He works with the director of mission. So that's one functional area. Some of the other functional areas are ORSA, which is Operations Research and Systems. There is some manpower kind of things that look at kind of manpower projecting. There is strategic intel officers. There's a lot. Functional Area 52 was the most interesting to me. Functional Area 52 is a nuclear and counterproliferation officer. So our duties range from everything to writing nuclear policy. So, you know, typically a new administration comes in. Previously, the Trump administration, before that, the Obama administration, both released I can't think now what the name of the document is, but they release a document at the start of their administration that kind of outlines how they're going to use nuclear weapons and what their nuclear policy is and all of that. FA-52s are involved with writing that strategy. So they're policy applications. There are also technical applications. So some of the jobs are working with the Defense Threat Reduction Agency, Nuclear Posture Review. Thank you. Yes, the NPR. So there are 52s that do more policy type jobs. I'm more of a technical type. So the jobs I've had previously have been as a nuclear weapons effect officer stationed at USANCA at Fort Belvoir, Virginia. So we looked at things like, if there was a nuclear battlefield, you know, the Army's the most likely to be impacted by that. How does the use of nuclear weapons on a battlefield impact the Army's ability to conduct maneuver? You know, if either an adversary or the United States uses a nuclear weapon in combat, how does that change the scope of the battlefield? How are we able to maneuver? I'm also trained in things like HPAC, so using software to kind of model some of those nuclear weapons effects and show plumes and fallout and things like that. Yes, the Army's NDT teams, they are also FA-52s primarily. There's some other things that kind of go in there. They also have some EOD, explosive ordnance device officer, but the NDTs there at the 20th Suburni are FA-52s. Most of our billets, most of our jobs are within the DC area. So DITRA, the NDTs, STRATCOM, a lot of our officers work in STRATCOM doing nuclear targeting and things like that. Does that sort of answer your questions?
Yes, that does. And I guess one follow-up question. So are you teaching at West Point right now, or are you working? Okay.
Yeah, so I am. That's another job that 52s do. We do teach here at the United States Military Academy. So I am currently an assistant professor teaching. This semester I'm teaching 496, which is the second semester of the senior design capstone for our ABET accredited undergraduate nuclear engineering program. And then I also teach NE 355, which is the reactor theory course. And in the fall, I usually teach NE 300, which is the Welcome to Nuclear Engineering, and 495, which is the first semester of the capstone course.
Got it. Thank you so much.
No worries. Yeah, so kind of our things are, you know, education. We do some RDT&E, kind of research development training. And then we have policy people who work, you know, at very high levels. Some of them, you know, direct advisors to like the strategic command and things like that. And so those are kind of all our kind of lanes that we work in. Thanks for the question. Well, if there's not any more questions, I really appreciate everybody's time. Dr. Hines, I'll turn it back over to you and let you close out. But thank you all for your time, and hopefully you got something out of it. I'm sure my email was somewhere in one of these links. If you think of any questions or have any comments or concerns, feel free to email me. Thank you all.
Dr. Baker, thank you from the Nuclear Engineering Department. Let me also apologize. I think when I originally introduced you, I said Lieutenant Commander Baker. That comes from my old Navy days. I know that translates to a major, which is a rank below your major. So I didn't mean to de-rank you there. And I apologize.
No worries, sir.
Colonel Baker.
One of those things, you can call me whatever, just don't call me late for dinner. So I knew what you meant. Thanks.
Okay. Well, thank you very much, and have a great day. Bye-bye.